The answers to question number 8. Magnetism. Number 1, a proton travels through a potential of 1 kilovolt and then moves into a magnetic field. So from the given potential, you got to find the kinetic energy of the proton. Remember that if it is accelerated through 1 kilovolt, then it has a kinetic energy of 1 kilo electron volts. So use that to find the velocity. Q times the voltage is 1/2 mv squared. Rearrange that to get the velocity. Charge of the electron is 1.6 times 10 to the negative 19. Voltage is 1 kilovolt, which is 10 to the 3. And that's the mass of the proton. On calculation, that gives 4.37 times 10 to the 5 meter per second. Now to calculate the radius, mv divided by qb, m is the mass, velocity is 4.37 times 10 to the 5 divided by the charge of the proton, which is the same as the charge of the electron, times the magnetic field, which is 0.040. On calculation, that gives 0.11 meter. In the second question, the two wires are carrying currents of 10 ampere in opposite directions. They are separated by 40 centimeter. You have to find the magnetic field in the plane of the wires at a point that is 20 centimeter from one and 60 centimeters from the other. So that's one, that's the second conductor. Both are carrying currents in opposite directions, as you can see. And we'll call this, the current is 10 ampere there, and 10 ampere in the other. So this is the point that, would be 20 centimeters from the red one and 60 centimeters from the blue one. Now that gives the direction of the magnetic fields that they produce, because you know that the magnetic field is given by the right hand grasp rule, where the thumb points in the direction of the current and the closed fingers to the tips gives the direction of the magnetic field. So obviously the magnetic fields at that point are in opposite directions. Now the magnitudes, the formula is mu naught by 2 pi I by d, but mu naught by 2 pi is common, can be taken out. So I1 by d1 minus I2 by d2. Mu naught is 4 pi times 10 to the negative 7. I1 10 ampere, distance 0.2 in meters, and for the other one it's 0.6. So on calculation it gives 6.7 times 10 to the minus 6 Tesla. In the third question, which is similar to question 1, the proton is accelerated through 500 volts and then enters a magnetic field. You define the radius. Again, Q V is equal to 1/2 mv squared, and therefore the velocity can be found. It is a proton which has the same charge as the electron. The voltage is 500 mass of the proton is 1.67 times 10 to the negative 27 kilograms. And calculating that yields 3.09 times 10 to the 5 meter per second. And then the radius is mv by qb. Mass of the proton times the velocity that we got right now, divided by the charge, times the magnetic field, and that gives 1.1 times 10 to the negative 2 meter. How many turns should a 10 centimeter long solenoid have if it is to generate 1.5 millitesla magnetic field? Direct equation: the field due to a solenoid is mu naught Ni by the length. All terms given, rearrange. N is the number of turns, of course. B is 1.5 times 10 to the negative 3. Length must be in meters, so that's 0.1. V naught is 4 pi times 10 to the negative 7. And the current is 1 ampere. That gives 119 turns. Fifth, the electron is moving with a speed of 8 times 10 to the 6 along the positive x-axis. And then it enters a region where there is a magnetic field of 2.5 Tesla directed at an angle of 60 degrees to the positive x-axis. So now you define the force, it's QVB sine theta. That is the formula for force on a charged particle moving through a magnetic field. Electron, charge of the electron times the velocity given, multiplied by the magnetic field, and sine of 60 degrees, which gives 2.8 times 10 to the negative 12 newtons. Again, a problem about a solenoid, direct formula. That's mu naught. Number of turns 500. The current is given as 10 ampere by the length must be in meters, so 0.20, and that gives 0.31 Tesla. Once again you have a similar question where you have a beam of electrons accelerated through a particular potential difference, and then it enters a velocity selector. You know, a velocity selector is where the electric field and the magnetic field exert equal and opposite forces on the particle. So that's the idea, but the velocity is not given here, so first you find the velocity using this idea as before. Find the velocity. Yeah, the voltage is 10 kilovolts. That's why it's 10 to the 4, which is 10,000. And once you get the velocity, notice that it's a real high velocity. Once you get that for a velocity selector, it's the ratio. Velocity is the ratio of the electric field to the magnetic field. So to find the strength of the electric field, multiply the velocity with the strength of the magnetic field. That gives 5.9 times 10 to the 5 volt per meter. Eighth one, it's a circular loop. The radius is 0.5 meter. It's a uniform magnetic field. The current in the loop is 2 ampere. You're asked to find the torque when the plane of the loop is perpendicular to the magnetic field. You see, if the plane of the loop is perpendicular to the magnetic field, that means the angle made is 0, because we always take the angle with respect to the perpendicular drawn to the coil. Since the angle is 0, the torque is 0, because torque is given by NIAB sine theta. NIAB sine theta, theta 0, sine 0 is equal to 0. Look at the figure and try to understand. Remember, angle is always of the normal. Normal means the perpendicular with the magnetic field. It's not between the plane and the magnetic field. Here, same problem, but this time the plane of the loop is parallel. So if the plane is parallel, then the angle is 90 degrees. Therefore, tau is NIAB sine theta, sine 90 is 1, that's why it's missing. It's a loop, so number of turns is 1, 2 amperes, and of course the area is pi r squared. And on calculation that gives 0.47 meter Newton. Two parallel wires carry currents of 20 and 5 in opposite directions. At what point between the two wires are the contributions of the two wires the same? So we're looking for a point where the magnetic fields are equal. 20 ampere and 5 ampere, and they are separated by 0.20 meter. The strength of the magnetic field is given by mu naught by 2 pi I by d, and here the two have to be equal, so B1 is equal to B2. Cancel the terms, similar terms from both sides. Rearrange and calculate D, for which we'll have to cross multiply, distribute it. .16 meter. Again, two long parallel wires carry currents 5 and 8 in opposite directions. Find the magnetic force per unit length. This time we got to find the magnetic force. Remember that these questions have not been worked out for university physics students because it's in the next chapter. So this is actually a quiz for college physics students. So the force is given by F is mu naught by 2 pi I1 I2 by d times the length. But it says find the force between, for unit length, which means for 1 meter, and therefore L is 1 meter, and we can calculate all the remaining quantities that are given, and you would get the answer. And the formula is the answer is 2.7 times 10 to the negative 5 newtons, and it's going to be repulsive because the currents are flowing in the opposite direction. Here an electron is moving with a speed perpendicular to a magnetic field. What's the magnitude of the magnetic force? F is equal to Q VB sine theta. Theta is 90 degrees. The force is maximum. Put the charge of the electron, multiply with the velocity. The magnitude of the magnetic force can be easily found out. You get it as 1.6 times 10 to the negative 15 newtons. Here you have a thin rod, length given, mass given, and it's in a magnetic field. And the question is, what current should pass through the rod so that its weight is cancelled out? The weight of an object is mg, and the force is bi times the length. So set them equal to each other because they are equal, and calculate the current. Mass times acceleration due to gravity divided by the strength of the magnetic field times the length. Get 4.9 ampere. In this question, okay, this is a force of 6 times 10 to the negative 3 Newton I, and then it has a J and a K. So the force has 3 components, velocity has 2 components, and this question need not be done by college physics students. Remember, this is calculus based. Okay. To find the components of the magnetic field, we know that F is Q V cross B. Excuse me. The force is given. Write the whole thing down. And then you have the IJK. First you put the velocity components, that is 2 times 10 to the 6 and 3 times 10 to the 6. And it has no K component, so you have BX, BY, and BZ. Then you take the cross product. Remember that the J is negative. The K has both. So got to be really careful when you write those down. And then you look at the right hand side and distribute the 2 times 10 to the negative 9. Now that's putting the 2 coefficients of I on either side equal to each other. Let me explain that, because when you look at the coefficient of I, on the left hand side you have this 6 times 10 to the negative 3, that's the coefficient of I, and on the right hand side the coefficient of I is 2 times 10 to the negative 9 multiplied by 3 times 10 to the 6. That's the coefficient of I, BZ of course. So that's why I've put them equal to each other, from which you can calculate BZ as 1 Tesla. And then again put the coefficients of K on either side equal to each other. The coefficient of K here on the left hand side is 8 times 10 to the negative 3, and on the right hand side it is 2 times 10 to the negative 9 times 2 to the 10 to the 6 by, because the x component is already given as 0. So when you put those two equal to each other, you get by. Now therefore the magnetic field is minus 2J plus 1K. In the 15th question, again, an electron is moving, entering a region where there's a magnetic field, 7 millitesla, velocity, and you have to find the spacing of the circles of the helix. This is a problem where you have to consider the velocity having both perpendicular and parallel components. Remember that the magnetic field is along the k axis. Therefore, the parallel component of the velocity would be 5 times 10 to the 6, and the perpendicular component of the velocity would be 7 times 10 to the 6 meter per second. Now, to calculate the radius, use the perpendicular component. So you go with mass of the electron times the velocity. We're taking the J component because it's at right angles to the magnetic field. So that's charge, and the strength of the magnetic field is 7 millitesla. That's why it's 7 times 10 to the negative 3. Once you get the radius, you find the time period of rotation, which is circumference by velocity. We got the radius divided by the same velocity along the j-axis, and you get the time period. And remember that to find the spacing of the helix, we got to multiply this time with the parallel component of the velocity. Okay. And the parallel component is that which is along the k. So it is 5 times 10 to the 6 times this time, which is 5.12 times 10 to the negative 9. That gives 0.0256 meter. So that's about 2.6 centimeter. In the 16th question, a circular loop is carrying a current and is in a magnetic field. The area of the loop is given and it's oriented at 37 degrees. But look at it, it says it's plane. It's at 37 degrees. We never take the angle with the plane. We always take it with the perpendicular. Therefore, the angle is not 37 degrees. It's a loop, so the number of turns is 1. Current flowing 2. Area is 0.12. B is 3.5. It's sine 53. Why? Because the angle is 90 minus 37, which gives 0.67 meter Newton. Thank you.